Hey everybody, so this particular research paper is called Self-Guided Action Diffusion, and it's put out by Stanford University. And up front, it hasn't been peer-reviewed yet or anything along those lines, but the thing that catches my eye about this particular research paper is the method that they have developed, and then the use case I care less so about, but perhaps you'll care more about it. But we can dive into this research paper. So essentially, what they have done and what they've created, they call it SelfGAD, so self-guided action diffusion. And essentially, the big problem within diffusion overall is and with models when it comes, not just with diffusion, with AI models overall, is this temporal dependencies issue, right? And then so diffusion models can handle temporal dependencies, this right here, far better than say transformers models or anything like that. Diffusion models are kind of more built for this overall from the ground up. But the problem that diffusion models run into is policy steering, right? They don't have the same kind of internal reward mechanism that you find in other types of AI. And then so their approach is essentially that they create a gradient-based steering mechanism in diffusion in order to solve that. So they put gradient descent inside of the diffusion mechanism, essentially overall, right? And then so you can see here, so I think this is a good representation overall. So you see this state encoding, and then you get this output, which is guided action. LLM models are very bad at this specifically, and this is what people want them to be, right? People want them to be agent-based models, but they're not good at this. Whereas in diffusion space, essentially we compute a weighted Euclidean distance between predicted and prior trajectories, applying gradients to guide model outputs, interpolated between two denoising paths. The green arrow represents the prior action, while the red arrow denotes the predicted action, iteratively refined through diffusion denoising with guidance applied at each step. And then they go through the math and the policy, etc., right? But so their particular output and what they're testing this for is for robotics very specifically, right? And then so they put it through their model through robotics tests, and then so block push, kitchen, lift, and then push T, and they have the averages of that. And then that's what all of their testing is around this. And then so you can see here's kind of the real world test, and they have their robot that they're training via and fine tuning via this method, right? And then so the point of this method overall is that these environments are noisy. Like a kitchen counter is noisy, a stove is noisy, it could be different stoves, same with a sink, right? Microwave, etc. These are hard tasks because it's once you take the model out of a perfect environment, then it becomes harder and harder for the model. And then so with this particular diffusion-based method and this particular guided diffusion-based method that they've built out here, models are able to score very well on these tasks overall, which, going back up to the top, because very specifically, diffusion models have an advantage when it comes to this as opposed to other architectures, right? And then it's just been a matter of this. And then so they put this into, and you combine it with this, and then you get very awesome, very nice results from that when it comes to agentic action. And then these models handle agentic action overall very differently than a transformers model. It's hard for a diffusion model to hallucinate API key, for example, things like that, right? It just flat out won't do it. It's not part of the architecture within that. And then so again, this particular research paper here, all of their focus on and around this is via robotics. But you can take this same exact what they've built out here, and then if you trained a diffusion model on it utilizing their framework, I'm 100% positive that you would be able to utilize this and then have it work for agentic frameworks. And then my estimation within that would be that this particular type of framework would significantly outperform LLM models, existing transformer models, etc. The problem with that overall is that diffusion models are very expensive to train from the ground up. And then so in order to test this theory, it would be very, very expensive and very, very computationally expensive just to even test it out, right? There's no way that we could test it out just casually. But what we can test out casually, and then so what I've built out based off of this paper is a swarm-guided action decoding decoder, or SwarmGAD. And then so essentially I've taken their GAD framework, so everything that they've laid out, and then they have essentially like a diffusion decoder within that. And then so I just replaced the diffusion decoder with a swarm-guided action decoder. So it's essentially just replacing that particular unit. And then this is a concept that I've gone over previously on this channel kind of multiple times, that you can utilize the swarm algorithms to mimic and essentially perform the same functions as diffusion models, but just with it's far more computationally efficient to do it. So this is kind of like a simulation of my hypothesis that this particular research paper and what they're doing here would be very nice and very good for actually training like a diffusion agent based model, right? And then based on API calls, API functions, etc. And then so to prove that out, this notebook introduces swarm guided action decoding, or SwarmGAD, a prototype framework that blends swarm intelligence with the idea of self-guided decoding to solve structured planning problems. Inspired by diffusion style action refinement, the approach replaces the diffusion sampler with a particle swarm optimizer enhanced by a prior guided consistency term. The core concepts within this: the swarm optimizer with self-guidance. Each candidate solution is represented by a particle that explores the search space. Particles are influenced by inertia, cognitive pool, social pool, and self-guidance policy. Flexible domains. Optimizer can operate on images, text, structured actions, and structured action vectors. I give you the full code for all of that at the top. I'll show you, and then the actual demo in the second cell here. So as far as going through and executing this model, I'll show you the demo here. Essentially, we're going to go through and do a weather API call. So this is the SwarmGAD framework here. So this top cell is just the generic framework. You can plug it in for whatever you would like it to be and finalize in the end, right? And then so this is just if you want to play around with this particular framework and then you want it to be actually computational efficient, here's everything built out for you in order to do that. And then in this second cell, I want to test that hypothesis that I've laid out here related to this research paper, and the reason why I'm personally talking about this research paper and it caught my attention, in that I think that this method could be very strong for agent-based actions, right? And then so in this instance, I utilize this SwarmGAD to become an API planner and caller. And then so in this instance, we're going to utilize Weather API just because I don't need any sort of API key or anything like that in order to test it out. And then so we're going to call, and then we have our, we want the model to summarize the weather. So a current temperature, weather code, we're just giving it essentially the mapping data that it needs in order to understand and put these calls together, right? And then so then we have it essentially plan through, and then its plan is to create a geocode, a forecast, and a summary, and that's kind of what it does within that structure overall. The three models, this is think a planner, executor, and coder is kind of that, that type of framework is exactly how this is set up. And then so you run through, and then so you can see, so essentially it's planning, and then it shows its plans and its tools. So geocode, forecast, and summarize. And then we have our arguments. I had it run, and then I ran the demo for San Diego here. And then so we get our output here, San Diego, and then it's mainly clear, wind speeds of 4.7, temperature of 18.4 degrees Celsius. Enjoy your day. And then I could change this to say Los Angeles or San Francisco, right? I could do that. And then we go through, and then so San Francisco is 16 degrees Celsius, so cooler. than San Diego, and then a lot more windy. And then it's so it's windy, so it's secure that you lose items. And then there you go. And then so it's able to pull this. It's able to, and then it's able to pull directly from San Francisco there as well as San Diego. And then just to be sure, let's go ahead and just do Los Angeles while we're here, right? Perfect. And San Diego or Los Angeles is warmer than both cities by a few degrees, and then a little bit windier than San Diego, but not much, far less windy than San Francisco. So enjoy your day. Uh, and then so there you go. And then so this is again like this is the model pulling this and then utilizing this for API calls and agentic actions, right? And then so that's what I want to highlight within this overall. Like this is like so currently as it stands right now, like LM and agentic based frameworks are getting about like 50% accuracy. Like I think that this overall, like this particular framework, my expectation is that it would slaughter any sort of like transformer based architecture that's out there, right? And then like I mean, that's exactly what this framework is designed to do. It's exactly how they built it out for. They built it out for robotic actions. But like, so API calls are simpler and easier than robotic based actions, right? And that's kind of where my brain went when first looking at this research paper. So if it could pull that off, I figure it would be able to pull this off. I can give you a proof of concept demo that like we're again this is simulating diffusion, right, as closely as I can, and it works. So this like would be very nice. The next step would be like I don't know, like hopefully something, maybe some open source company decides to train a diffusion model and then get into diffusion with regards towards agentic AI. Like it's an area that's unexplored, right? Like there's, to me, like at this point, I think like pretty much every avenue that could possibly be explored with regards towards agentic frameworks and transformers has been explored, right? That's why I talk about agentic frameworks like less and less on this channel, right? There's been nothing revolutionary for a few years now that has come out with regards towards agentic frameworks and transformers. I think it's a dead end there. But I think that this is like specifically like this and these types of things are the way to go within this. So I'll link to both this research paper and the collab notebook. And if you like this sort of content, please like and subscribe. Thank you very much.